Right. Hey, everybody. So we will start the next talk. Then we'll have the coffee break. We will probably ease into the coffee break a little bit. Um, so it's my pleasure to introduce Raj, who's an assistant professor at the UC San Diego, and also spent time, I think, at Mosaic ML slash Databricks and then NVIDIA. So he's also at places where things are happening and has seen things from both sides. And I came to know Raj from his hot takes on Twitter. And he said he will share more hot takes today. So let's see. Welcome, Raj.
All right, thank you. All right, so we're going to talk a little bit today about navigating the safety capability spectrum, especially when you're training agents with feedback. So I've been working at this sort of very specific intersection of reinforcement learning with language for the better part of a decade, and it's super exciting to see all the interest in this field today. Okay, so we spent about 3 days-ish, roughly, at this workshop. Who wants to tell me what an agent is? Surely we have some kind of a definition by now. Yeah, that's about what I expected. So especially if you spend as much time in the Bay as I do these days, the answer seems to be something along the lines of, an agent is whatever you want it to be. And honestly, like, I'm only half joking here, because if you ask 5 computer scientists a definition of an agent, you're going to get 5 different definitions. It's a little bit like asking biologists what life is at this point. So we can identify some key components of it, right? So, you know, grounding, agency, memory, reasoning, learning, these sorts of things. With the simplest version being something along the lines of an agent acts using tools in a loop in order to solve problems. So we're going to run with roughly this definition from here. Okay, anyone want to give take a crack at this one? What are reasoning capabilities? I feel like we've had plenty of speakers over the last couple days talking about this. So again, the answer kind of seems to be it's whatever you want it to be, with the sort of like very, very baseline ability of an agent that solves problems that require sequential decision making over multiple steps, right? So this is like the most basic version of these kinds of reasoning capabilities that we could possibly have. Okay, you guys literally just had a talk on this. So what is safety? It's like, imagine you're doing a pop quiz after Yoshua's talk. Right? So this is one where we actually kind of know. And it revolves from everything from having cybersecurity problems. So it's like, oh, well, you know, you have all these models that are being deployed, computer use, so on and so forth, that have very, very large threat surfaces. So doing things like preventing prompt injections into them, all the way to catastrophic X risk. And it really boils down to preventing undesirable outputs from these models. So the binary view is that you can either have safe models or you can have capable ones. And like the sort of like adage that you kind of see a lot here is, if company A wins the AGI race, you're going to have safe models, but they are lobotomized and they won't be as capable as they could be. And if company B wins the race, you will have really, really capable models, but it won't matter because we're all dead. Obviously, we're not the type to deal in complete absolutes here. And the way to think about this is, if you develop a safety method that trades off large proportions of capabilities in return for that safety, no one's going to use it. Right? The economic incentives are just not aligned for the current big players to adopt those kinds of methods. And simultaneously, on the other hand, if you develop a way of having models that are super capable, but the way that they explore the world in order to do so is very risky, that is also not going to probably be adopted. And then the key point across all of this is that any method that you develop along this sort of spectrum needs to be scalable. So if you're talking about the safety end of things, if you're thinking about like scalable oversight, you need to have methods that are capable of monitoring in the order of hundreds of millions to billions of requests a day. And obviously I don't need to talk too much about scaling in terms of capabilities, right? Like we've all seen data scaling, flop scaling, so on and so forth. And so that's what we're going to talk about today. So specifically, I'm going to start from the sort of fundamentals where I'm going to think about building and developing these sort of like scalable safety capability levers. And then talk a little bit about applying those levers to exploring in grounded simulated environments and also a bit of the real world. And then a little bit about where we've been going from here. So thanks to all these wonderful sort of spaceship builders today, I'm going to spend first a bit of time talking about the actual levers that we have. Okay, so as a bit of like an intro recap, we've seen like the push towards interactive models quite a bit these days. Say you as a person ask a model to do something for you, right? In this case, give me a movie review, no matter how like negatively this starts. And if like the model doesn't get it right, you can give it feedback. The simplest form of this feedback is this thumbs up, thumbs down. You can kind of like expect, as complex feedback as you want. But generally speaking, the model's like job is to now use this feedback and try to use it to improve its response. And so at a high level, the task is really, hey, let's optimize an arbitrary non-differentiable score that comes out from a system that outputs things one at a time in a sequence. And reinforcement learning is basically what this was like. This was the like use case for RL originally. And so we're going to talk a little bit about like applying RL in these kinds of domains. So a little bit of again, more recap on the VLM pipeline that the big companies are all kind of doing right now. The LLM and the VLM, the vision language pipeline are actually really quite similar at this point. So you start off with basically taking your entire internet scale data, you spend a lot of time and you carefully curate it, and then you throw it into your favorite objective, usually next token prediction, and then you go from there onward, right? It's like encoding all the knowledge of the internet. And if you're especially fancy, you have something called a mid-training team, which is basically focused on curriculum learning, sort of at the tail end of that pre-training, to upweight or downweight various like domains that you as a company care about. You then collect 1 metric ton of human demonstrations, which is just people teaching these models exactly how to say or do things for the sole purpose of behavior cloning, which is just like what the RL people call supervised learning in this case. And then from there, you either are collecting human feedback, so the model then gets deployed, you're collecting human feedback, or you're creating some kind of interactive environment for these models to act in. Then you're training a human proxy reward function or designing environment rewards. You train a policy, which is just the agent using RL until your reward saturates. And this cycle loops. And at this point, like I think the average sort of like life cycle span for these kinds of things is in the order of 2 to 4 weeks, where you have new model deployed, new set of like preferences collected, and then like rinse and repeat. And so what are the levers here, right? So there's actually a bunch of different sort of like areas of this pipeline that you can kind of like focus in on to think about what you can do to tweak the behaviors of these models. So my lab and collaborators and I, we have results actually basically across like all of these, but I'm only going to talk to you about like a few of them, right? So they range everything from, the model priors. So it's like, oh, what does the checkpoint that you start doing RL from actually look like, right? What was the mid-training data and this supervised fine-tuning data that went into it? What are you doing with the rewards? How are you scaling your rewards? How did you design your environments? And then what are you actually doing at the end with RL training, right? What does your RL engineering infra actually look like? So the first thing I'm going to talk to you guys about is the rewards. And so the motivation here is that a lot of like the RL that you see happening in the sort of agents and the RLHF use cases are single rewards at the end of a very long sequence, and that's it. It's one very sparse reward. And there's been like a lot of talk about whether this is like really RL, is it really not RL, is it actually just a multi-armed bandit problem that's taken a new form. And there's been a bunch of recent results as recently as last week with like thinking machines showing that policy gradients really only learn like 1 bit of information per episode in this. That seems super inefficient. Can we make that denser? All the RL people know that like making a reward denser generally tends to help things out. So how do we do this, right? And if you think about it, every single one of these like learned reward models is doing only a single forward pass across this, whereas the actual generating models that are generating the answers are doing many, many forward passes. They're doing all this like long chain of thought. They're doing self-consistency, what have you. Why are the reward models not doing this? And with that motivation about 2 years ago, though we actually only were allowed to publish it about a year ago, we started working on having reward models that scale with additional inference time compute. And the concept goes a little bit like this, right? So the user asks some kind of question. There is a generating model that responds with an answer. You send it to the critique out loud reward model, or cloud in this case, and it generates a critique of what the response is. And then based on that critique is conditioned, you get a reward model or reward scalar score that pops out of this. So this is really like trying to combine the best of both worlds of using these kinds of like LLM as judges as well as standard Bradley-Terry-based reward models. And so a little bit more in depth, the sort of key component here is that in order to be able to make use of these models that you have actually need to be able to generate coherent critiques. So when we first did this like a couple years ago, we were doing this on a bunch of internal models plus like Llama, and there's some like Llama 3s, and they were somewhat okay at generating critiques, but they really need like quite a bit of help. And so the first thing you do is you collect Oracle data. Which is either humans or nowadays, like because the base models themselves are a little bit better, you can distill of what these critiques actually look like. And then you can fine tune the base LLM on these critiques. And then you have it generate like a ton more of synthetic data of it itself generating like more critiques. And then from there, it's simple. You simply initialize another head on top of the existing model. You have a new reward head, and then you simultaneously train the LM head with the SFTing on the critique loss, and then the reward head by preference modeling on whatever your reward data set is, and then out pops your cloud reward model. So when we tested this about a year or two ago, reward bench was the then going like best sort of benchmark for reward models. And you can kind of see this kind of like critique out loud method, the sort of like dual Bradley-Terry plus LLM as a judge works significantly better than all sorts of like classical like methods. And more importantly, if you optimize a policy against this kind of reward, they tend to outperform these classical reward model optimized RLs policies on downstream evals. In this case, what you're looking at is like an eval for Arena Hard, which is a subset of LLM Arena that focuses on like hard coding and math reasoning sort of tasks. Okay, so if you notice the reward that this model like sort of pops out at the end, you have the critique, but it's still in the form of a single scalar. And the key problem here now is also that human feedback is inherently multidimensional. right? So every single sort of like, sentence, you might not like it for one reason, you might like it for another reason, so on and so forth. And then like I was saying earlier, like condensing that all down to a sort of a single scalar that's at the end of a very long sequence just gets you lots of like stability issues and so on and so forth. So a couple years ago, we had this sort of like more academic work where we were trying to figure out how to have fine-grained or processed dense reward models. And our way of doing this and collecting the data for this on doing like multidimensional rewards is we would give a prompt and then a model-generated answer, and we would ask these human crowd workers to highlight a span in the text and then identify from a list of categories what kind of error that was. Right, so, okay, like this particular piece of text is not factually correct, it's not irrelevant, so on and so forth. And then, you could, in theory, you could get something beautiful like this, right? You could basically, at sort of subsequences, you could actually get like, multiple reward models giving you dense feedback along the way. And this worked, and we collected in the order of like 10-ish thousand human feedback samples. And then I was at this company called Mosaic ML that like got acquired, and suddenly we had a budget that like, was around 50 to 100x larger. And so I spent the next 2-ish years like figuring out how to scale this when you actually have a crowd worker pool that is in the order of like, 100 to 200K people. And it was pretty clear that the dense rewards were showing improvements. But seriously, like getting people to label that amount of data cleanly at a very large scale is nearly impossible. I'm like not allowed to say like the crowd worker companies' names, but like a lot of the data is quite bad. Right? So that's the sort of like first kind of issue that we ran into. And then the second issue is also, if you think about it, like if you're just adding up all the rewards at different points in the sequence, you can possibly lose information. I like to think of this in terms of like wave interference, right? If you have, a +1/+1 reward at a particular point in the sequence, they kind of reinforce each other. But if you have one reward that says +1 and another reward that says -1, they sort of like collide together and cancel out. And so that's where the next axis that we've been sort of developing on, and the lever we've been developing, is figuring out how to do this kind of training from the perspective of task diversity, of being able to do like multi-objective training. And so, this paper, we put it out on like arXiv about last week, so this is like super hot off the press. And what we tried to do was we tried to get a pretty wide range of domains across the sort of verifiable to like non-verifiable spectrum. So we did everything from math, which is just the Dan Hendricks math data set, but it's sort of modified instead of just doing like accuracy to being like, oh, can you also like do the math well and be able to explain it well. We did multi-turn dialogue, which if you look at this thing called like Socratic mind is actually it's multi-turn dialogue in the order of, in my classroom, I'm going to replace all clicker questions actually with an AI, right? So it's people talk to, like I ask a question, people talk to the AI system, and the system says, oh, your answer on this part of the question was right, but can you explain a little bit more on this like other part? And this is real data. I've run this in my actual classroom at UCSD for the last year, and there's been a bunch of other professors at Georgia Tech that have been running it too, so this is in the order of like 100-ish K, actual real interactions with students. And then the final is things that are a little bit less tangible, right? Less verifiable, so to speak, which is human values, which is these two data sets, one of which was NVIDIA developed, and that are sort of regenerated with modern models. And so I'm going to use the example of math and then give an example of how to scalably train a process reward model or like a fine-grained reward model. And then the recipe that seems to work is what you do is you first take your reasoning reward model, your cloud basically, and you calibrate it on a small amount of human outcome data. So the key here is you do not ask people to label the process. You simply ask people to label if the outcome that the model has is something that they liked. And this is still like not an easy problem to do, but it's a lot more tractable than trying to get dense feedback from people. And then what you can do from there is you can do sort of Monte Carlo rollouts starting at various steps in the reasoning process, and then use this reward model and then do like majority voting there, and then bootstrap the values from there. So like a little bit of a more visual is that like, so say you have the prompt, the model is doing like, multiple steps of reasoning, and then at the very end, once you get to the final step, you have your cloud that sort of like labels the trajectory, and then you can kind of go back up this tree almost like Monte Carlo fashion and kind of label what the values are. And then now you have this like giant synthetic like data set, right? Of process reward model sort of data set, which is, here's what the target value should be, and you can turn that into a loss function to train your PRM here. So that same exact kind of method, you can actually apply to all of these like cases. The only thing that really changes between math and the human values and the dialogue is the data that's collected from the people at the end of like what outcomes they like, and then what the sort of like processes are, like what counts as a step, so to speak. Right, this is like pretty clear in math. In multi-turn dialogue, it's just every turn of the dialogue can count as like a different sort of step. And then for human values, you can kind of like break it down into chunks here. And so we collected a bunch of data, again, of this type. We trained, PRMs with this. And like we somewhat like evaluated them. And the general gist of what you're seeing here is it actually turns out that like, so we had all these like dimensions, right? We have like, the PRM is doing accuracy labeling on math, engagement labeling on math, helpfulness, honesty, truthfulness, and then for student like AI tutoring kinds of use cases. And training individualized reward models seems to work a little bit better in general, but you can kind of shove all the data together, and then you can train sort of one PRM across everything, and that is reasonably good enough for a lot of like RL use cases on top. Okay, so now that you have the PRM, what are you actually doing with it? And like the correct thing to do with it is you do not throw it, like I was saying, you don't put it all into like one single scalar value, right? You want to vectorize your rewards, right? So you want to keep the rewards that the model receives during RL training as a vector, with each one of these like representing a different dimension. And if the reward is a vector, it helps for the policy, the actions also to be vectorized. And the implementation of this is relatively simple. You're basically using a shared LLM backbone, and you just have like multiple like heads on top, right? You can have multiple heads. These can be like different LoRa's, low rank adapters, like what have you. We've tried a few versions of this. They all work reasonably well. And you can train like the individual like heads separately, and then kind of combine them all together to update the sort of shared backbone. But actually, like in practice, you can actually get rid of the loss that goes to the backbone, and it still works reasonably well. And you can also do inference time scaling with this, right? So this isn't just a pure training time scaling. So what you can do is at inference time, you can combine sort of parallel and sequential thinking. So like I was saying, it's actually fairly similar to the labeling process earlier. At every step, you generate your, sort of your best of n like candidates. You do majority voting to figure out which your best next candidate is based on some like weighted sum of scores from your multi-objective PRM. And then you carry that onwards, and then you keep doing this, right? So you're sort of combining the chain of thought with best of n here. And this is actually really still fairly efficient from an engineering perspective. We took a while to get the engineering of this right, but like you can actually just carry forward all the KV caches because you get prefix caching. And yeah, like once this is efficient, this becomes quite fast at inference time. And then what you have are these like weights between the n vectors of like figuring out how to combine them together. Now you can either handcraft these or you can kind of learn them per prompt. I'm like not going to cover that much in too much detail because there's a couple of other papers that are out there that talk about how to do this. But what I do want to talk about is, it's a little bit, that's it for methodology, but I was talking to you guys earlier about how could possibly be like trade-offs here, right? And so what you're looking at here is in the sort of math case, we're looking at like varying the weights of the two like reward heads between getting it right and making it so that it's like engaging for a particular student. Right, and as you increase the weight of the engagement head, you can kind of see that like the engagement like scores that are sort of like students think is good increases. But if you look at the x-axis, like the absolute trade-off is actually not that much, right? And so just to sort of like drive in that point, right? That was a like somewhat destructive interference, but you don't always have destructive interference here. And that's the thing to take in mind. So what you're looking at over here is this sort of human values like kind of use case where you have the model being optimized for honesty, truthfulness, and helpfulness. And you can kind of think of helpfulness as the capabilities one, and honesty and truthfulness as being sort of more safety related. And so at the very center, like what we did was we had these sort of 3 reward heads, and you can kind of just like tweak the weights of the reward heads and see like what's going on here. And if you use any single one of the reward heads by themselves, like you see in the orange, green, or like red at the very center, you get some amount of scores. And the second you start using even 2 out of 3 of these heads together, or all 3 of these heads together in some linear combination, performance improves across all of the dimensions. And so what this is telling us is that you can have constructive interference. Safety and capabilities are not always a destructive trade-off. In some cases, the capabilities that you want the models to have are, fairly well aligned to safety. So what are the takeoffs of sort of this part of the talk here? Is that, some of these objectives clearly conflict with each other, some align, but the key thing to do when you're designing them is reduce the points of potential conflict where they can cancel information out from your sort of different objectives. And one way of doing this is by vectorizing your rewards and observing these kinds of like learned weights across them. And then, you can do this across like training, you can do this across inference, you can kind of stick them together and you get like both. But all of these like are significantly better than throwing it all into a single head like MLE blender and expecting a one-size-fits-all solution for your reward data sets. Cool. Okay, so I spent a little bit of time talking about how you do these kinds of things from human feedback. And in the next 10, 12 odd minutes or so, I'm going to talk to you guys a little bit about applying these things out in actual grounded environments, right? So why do we need this? If you notice, like everything that I talked about so far still requires getting human feedback, right? Whether it's like outcome feedback or what have you at some point. You and I have talked to people before. We know they're generally not very good at telling us what they want. And so the case that I'm making here is that we would really like to have these agents that are able to go out into a world, autonomously explore, test their hypotheses, and learn from feedback in the environments. And so thanks to my students here, these wonderful pilots, we're going to do a little bit of this. And so when I talk about these kinds of like agentic situations, like what do I actually care about? This is the specific case that I care about. I care about having like grounded embodied language agents, which is like, oh, you have a robot that you can kind of go and say, make me an omelet, it'll go do things and then come back to you, and you can give it a reward, what have you, right? And obviously creating these kinds of agents requires these sort of two main challenges, which is, can you plan out how to do this particular task in the world, bootstrap from the sort of like wide spectrum of internet knowledge that exists and plan it out. And then two, can you, actually execute these actions in the world? So for the purposes of the talk today, I'm mostly going to talk about the first bit, which is the high-level planning, right? It's like moving around in a world, perceiving, and then performing some actions via API calls to a low-level robot. And the underlying problem here, as I mentioned, of using world knowledge is really this problem of how can you get these agents to interact intelligently with common objects and other people in the world around you, right? So you or I, if we come across an object like a mailbox in the world, know that the correct way of interacting with it is to open it instead of trying to like chew it open, right? And then, similar sorts of things when we come across people, like we would not address, royalty as my dude unless you had a death wish. And at a sort of single step level, this seems to be fairly simple, right? It's like, oh, like the LLMs and stuff like do really well at this. Like, why is this not a solved problem? And the issue is that like when you start composing them across like very long sequence horizons, the problem becomes exponentially more difficult, right? So even if you had a classifier that gave you 99% accuracy classifications of the action to do at every single step, about a minute out for like some kind of a robot sim, you would already be at 120 steps, and so you'd be at 0.99 to the power 120, which is less than 30% accuracy across the whole trajectory, right? And that motivates like the sort of like next lever along, which we've been developing and scaling along, which is that of environment complexity. And specifically, the thing that we were doing is scaling along the length of horizon length of these kinds of systems, right? So say, like you have these kinds of like household, make a recipe in a house for a robot kind of situations. What we were doing is we were making the tasks more difficult by doing things like increasing the size of the number of rooms in the house, the objects, the things that they have to actually like interact with. And this is somewhat inspired by classical, I guess, like needle in a haystack evals that people have been using for long context, where you have like, a few million pieces, like tokens of context, and you're trying to identify the piece of information from there that, is actually like relevant for what you want. But first, like nobody's really done this nobody's gone into the multiple millions of context length for anything remotely related to robots. And two, like we go further than this, right? It's like instead of just asking or answering like an interactive question, we are going further by asking them to actually solve the problem by executing actions in the world. And for those of you unfamiliar with how like control works in these kinds of like environments, it's sort of like a one-slide primer on how vision language action models work. And basically, as you might imagine, everything is still a sequence. So you start off with like by tokenizing the actual like language, which is the language instruction. It's like, oh, go put the book on the shelf. You have the egocentric frames that the robot observes out in the world. Also like, tokenized, and then you have the actions, and then these kind of go into whatever have you simulator, and then the actions are just sort of API calls to the underlying robot. In this case, these are Canova, like 6 degrees of freedom, like Gen 3 arms, but you can kind of replace it with like whatever robot. So again, in the interest of time, I will show you some key results and takeaways from this to get you guys excited to read the paper. All right, so you can take this as like an advertisement for the paper. And so the first takeaway is this, right? So what we did was we trained agents on simpler environments, and then we zero-shot tested them on more complex environments, and you can kind of see generalization across this like complexity here. So what you're looking at here is like, so you can kind of see when I say like W203Q4, like what that means is the world size is 2, the object size is 3, and the horizon length is 4. You can train on that, and then you can transfer that exact policy to a much more complex world. And you see significant improvements in these VLA than the baselines, which is basically the zero shot of the actual like underlying models. Right? And then of course there's some like caveats here. You kind of have to get the rest of the recipe right, but we detail exactly how to do this in the paper. And not only do you see generalization as you increase complexity of the environment, you can see some amount of generalization across the type of tasks. So you can train on a subset of your tasks, which are things like pick and place like objects, and then at inference time, ask the robot to do things like clean, right? Clean in place, right? Like put it into a microwave in place, and it will be able to do these much more efficiently in a zero-shot fashion than like existing VLMs do from scratch. And of course, for funsies, we decided to test this on like SWE Gym, Software Engineering Gym, because I think there's been like at least half a dozen talks here who like probably care more about coding agents than they do about robots here. And it's the same exact recipe that we've been using for all the embodied planning things. And it turns out that like a lot of these, like not a lot, all of these results also hold when you're doing like software engineering style tasks, right? Where the tasks are sort of divided as like, you're fixing like pedantic issues, or you're trying to like merge in a PR with like very specific requirements on GitHub, right? So that was the good news. You can have these like recipes that work across domains. The bad news is that when you're trying to like look at long horizon length here, right? So what you're looking at here is like, for a bunch of different types of like models that you have, the x-axis is the horizon length, right? So like here we go from like 0 to 512K horizon length for truncation, and then the y is like, like it's sort of color coded based on, how much reward these kinds of like models get, or how many proportion of tasks they can complete. None of these work very well beyond the length that they were originally pre-trained for, which is usually like the 128K range, right? No matter like what all the sort of like, long context extension methods you use. This was pretty blackpilling for me in terms of all the context extension methods that are kind of out there. They just don't really work very well. And it becomes even worse when you're trying to get them to like do this multi-evidence case where you're trying to combine like multiple needles in this haystack together. Yeah.
What is the color? Like I'm confused of like the y-axis here is performance.
So the y-axis here is like you are going n steps through the particular task, and it's like it's performance. Can you get like 20% of the, so there's like checkpoints in the task of 20% of the way all the way to 100.
And then the color?
And then the color is like across a bunch of different tasks. What proportion are you getting? More green is more proportion.
Okay, thanks.
Yeah.
Sorry, while we're here. So like the top left, right, when you have this like pinkish thing between 60, I guess that's what, like 80%, and then it goes green to 100. How do I interpret that?
Which one you're looking at?
The top left. You've got this like slightly pink square, and there's center.
Right. Yeah. So the way to interpret that is like I guess it's a bit of an anomalous case where if you break it off at like 80%, like the models are not like doing well at that particular like section of the trajectory, but they're able to do well at the next section of the trajectory. Yeah. Yeah, and then this gets even worse if you have like instead of having like one single needle that you're trying to pull from the haystack, if you have multiple. And this is just sort of a different view of this. This is basically like reward curves of the rewards the models are collecting through time. The blue line being like the expert, which is a human planner in this case, and or like a classical planner with a ton of cheats. And then everything that you see sort of underneath is like one of these like models that we've trained with all sorts of like, or sort of existing state-of-the-art models with all sorts of like context extension methods. So there's really like quite a large gap in here. And so what does this mean for you, right? This means that a pretty important lever is being able to design these sort of simpler environments that quote unquote capture the essence of your task. And that becomes really quite important. And if you do that well, and you train on those, you're going to expect to see some amount of generalization across task types, complexity, recipes, and then these actual like techniques to sort of even travel across domains. But right now, you should not expect generalization to multiple tasks that are sort of composed on top of each other with super long horizon lengths. Okay, so sort of very briefly, now that we're in break, I'm going to talk about a little bit of what like my lab has kind of been working from here on out. And we've been really excited about the idea of scaling or like figuring out how to do levers along the line of like multi-agent communication. So everything that I've talked about in this sort of like talk so far has been single agent, but obviously like multi-agents, lots of people have been thinking about this from both the safety perspective of like, you have multiple agents that are sort of like debating with each other in order to arrive at a consensus for something, or, working together to collaboratively accomplish a particular task, right? So this is like thinking about the dynamic world as a unified decision-making framework. And so one thing that we've been super sort of excited about is this framework called MINDCraft. There's a bit of a name clash with a couple other papers at some point. But thinking about this sort of framework, which is in this embodied environment, where we have agents that are doing, cooking, construction, crafting, all sorts of like embodied tasks. And the key part of this is no single agent can achieve the task by itself. They have to work together by communicating in natural language. And actually, we started building this out about 3 years ago. We really only got around to like writing the paper 3 months ago. We kind of just threw this out on like GitHub, and it's gotten like a really large following. The Discord's got like 10K people, kind of all helping us with the engineering and adding new tasks and like figuring out exactly what is the right engineering structure for this. But the general gist of it is that like we did a bunch of like runs of trying to do these tasks with current, state-of-the-art models, have you like APIs or some amount of like, open source that are trained. And what you guys need to know here is that anything after 2-agent collaboration collapses completely right now, right? So like every single like model that exists can do at most like sort of 2-agent collaboration efficiently, unless it's like super scaffolded, and even then it's not particularly reliable, right? So the thing to think about is that like if we get all of these levers right and we get the recipes right, I would like to be able to create these kinds of like models that are everything from embodied helpers to the personalized tutors like we were talking about earlier, right? Like all of this is kind of in service of human AI collaboration here. So if you've forgotten everything else about this talk, let this be the 3 things that you remember here, right? The way to do this is you first want to think about developing these levers that trade off between safety and capabilities and making sure that they are scalable. And the second is that like, noting that these levers may not always lead to a trade-off between the two of them, right? There's plenty of use cases where, safety and capabilities are sort of well aligned with each other. And you can, if you get this right, you can have models that explore safely while improving capabilities. And then you're doing this all in service of the actual people that these models are going to be deployed to at the very end. So thank you. You can kind of get all these papers at these links, or if you just go to my lab website, like they'll all just be listed out over there. That's it.
Okay, maybe we'll take just one question, and then other questions can find Raj during the break.
Sounds great.
Yeah, please.
Thank you so much for the talk. I'm a bit concerned about your multi-collaboration when you talked about more than two agents collaborating. Mm-hmm. There is not enough information to understand the context in which you are talking about collaboration in this context.
Yes. So I can give a little bit more detail about that. So we tested a few different use cases. So think about like, a simulation of a cooking environment, like a restaurant or something, or like a construction case. So what we did was we tested two different situations where we tested peer-to-peer collaboration, where there's some kind of plan and the different agents know different parts of the plan, and they have to communicate together in order to, say, do things like make a building together, right? And really the key bottleneck here is that they have to be able to communicate what each one of them knows to each other and what the individual skills of each of the different agents are that are sort of specialized, and that doesn't work particularly well beyond two agents. The other version of this is we had like a sort of a manager-worker kind of a scenario where we had one agent that planned out, given a particular task from a human, the sort of steps that needed to be done, and then delegated these sub-goals to different agents. And then, the different agents had to kind of work together, given that they knew what the sub-goals were, right? So ideally, like, this is kind of how people work, right? I, as a lab manager, will, delegate, different sort of problems of things and so on. And it turns out that, like, this is also still fairly difficult, especially if the sub-goals have overlap with each other. Right, so if the sub-goals are sort of like all completely independent of each other and only require a single agent, the agents are doing okay. But for any of the sub-goals, if like two of the agents are working together, right, if they like both are required to like get the same resource, or if they're both required to like build the same part of the building, that communication aspect is not particularly well optimized for. In current models, and like the argument of the paper is that like we need to be optimizing for doing better, interagent communication, right? So that's I'm happy to talk more about this offline, but that's the sort of general gist of it.
Yeah. Thanks, Roger, again, and we will be back in 15 minutes at 11.